We've been talking about work where we considered a vector field a wind and a curve a trajectory that the wind was going to propel us along. Flux is very similar mathematically to work, however it's a very different circumstance. Now instead of considering a curve a trajectory, we're going to consider a border of an electronic component. And instead of considering a vector field wind, we're going to consider it the flow of heat. In this circumstance, if heat is flowing in the direction of the border, it's neither entering nor leaving and is not relevant to the temperature of the component. However, if heat flows perpendicular to the curve, it is now either leaving or entering the component and will strongly impact the temperature of our electronic component. So flux is a similar definition but a different direction that interests us. And flux is defined as the amount of a vector field that crosses perpendicular to the curve times the length of the curve or the distance of the curve. Okay. Let's look at a simple example where f equals 1, 2. The direction of the curve is 3, 4. And we have two perpendicular directions. Remember that the dot product equal to 0 means that they're perpendicular. So 3, 4 is perpendicular to 4 minus 3, which is a downward crossing, and minus 4, 3, which is an upward crossing. Okay. So our work in this circumstance will be f in the direction of the curve times the length of the curve, which is f in the direction 3, 4, which is f dot dir over the length of dir, 1, 2 dot 3, 4 over the length of 3, 4, times 5. The 5's cancel, and we get 11 joules. Now the amount of flux that's moving, crossing in an upward way equals f in the direction perpendicular to the curve, and that has an upward sense, and that would be minus 4, 3. So the upward flux is f in the direction minus 4, 3 times the length of the curve, which is 1, 2 dot minus 4, 3 over the length of minus 4, 3 times 5. 5 and minus 4, 3 cancel, and we get a result of 2. Okay. The flux going in a downward sense would be f in the direction 4 minus 3 times the distance, which is f dot dir over the length of dir. 1, 2 dot 4 minus 3, the length is still 5, the 5's cancel, and we're left with minus 2. This should not be a surprise. The amount of calories that are crossing in an upward direction should be the opposite of the amount of calories that are crossing in a downward direction. Okay. Oftentimes, electronic components are closed curves. So we want to define flux for the circumstance of a closed curve as the amount of the vector field that's moving outward or leaving the enclosed region times the length of the enclosed region. Okay? So this is going to be a circumstance of particular importance when we're working with flux. As with Green's theorem, we're now going to look at the amount of flux, outward flux that we have over a single rectangle where the corner point is xi, yj, its width is delta x, and its height is delta y. Okay. So our force vector field is f1, f2, and we're going to, along each curve, use the smallest value of x and y for determining what value of the vector field we use. So looking at L1, we're interested in the amount of the vector field that goes in a downward direction. For L2, we're interested in the amount of the vector field that goes in a rightward direction. L3, upward direction. L4, leftward direction. Okay. So let's start with L1, where the outward flux will be f dot 0 minus 1 over the magnitude of 0 minus 1. That's f dot down minus the magnitude of down times the length, which is delta x. And we find that f dot 0 minus 1 is minus f2 xi yj. Length is delta x. L2, we have f at the point xi plus delta xyj. And we want the component that goes in the direction 1, 0. So f dot 1, 0 over the magnitude of 1, 0 gives us f1 of xi plus delta x, and the length is delta y. So the amount of rightward or outward flux along L2 will be f1 x plus delta xy times delta y. L3, we want the amount of upward flux, so that's f evaluated at the point xi yj plus delta j dot 0, 1 over the times the length, which is delta y. And that gives us f2 xi yj plus delta j times delta x. L4, we want the leftward component of f times the distance. So that's f dot minus 1, 0 evaluated at xi yj times delta y. And that gives us minus f1 xi yj times delta y. Just as we did with Green's theorem, we can now group the two delta x terms and the two delta y terms. And we have f1 x plus delta xy minus f1 xy times delta y plus f2 xi y plus delta j minus f2 xy times delta x. We can once again put a delta x in the denominator and a delta x in the numerator, a delta y in the denominator, a delta y in the numerator, and now both of these will be set up for a difference quotient, and we get f1 x plus delta xy minus f1 xy over delta x plus f2 xy plus delta y minus f2 xy over delta y times delta y delta x. As delta x delta y go to 0, this becomes the partial derivative of f1 evaluated in xi yj. This becomes the partial derivative of f2 at xi yj with respect to y. And we end up with df1 dx plus df2 dy multiplied by the area. Okay. This is called the divergence, and soon we're going to do the divergence theorem. And this associates the outward flux around this closed curve with the area of the region. Now we've seen where the divergence can come from, and it turns out divergence is going to give us a very powerful tool in mathematics that's called the divergence theorem. The divergence theorem tells us if we have a vector field, as always defined by f1, f2, and we have a closed curve, and we want the amount of outward flux from along that curve, that can be obtained by integrating the divergence over the region enclosed within the curve. So if we want the outward flux along the C, we integrate over this sort of kidney-shaped region. If we want the outward flux over this rectangle, we integrate the divergence over this rectangular region. So to see why this is true, let's look at the divergence theorem for a very simple circumstance where we have a rectangular curve going from x equal 1 to x equal 5, y equal 2 to y equal 4. Our force is always, our vector field as always is given by f1, f2. And if we're interested in how much of, let's say, heat flow is leaving through this curve, the divergence theorem says we can integrate over the region, which is the integral from 1 to 5 dx, 2 to 4 dy, of the divergence, df1 dx plus df2 dy. So let's start by dividing this region into subregions. In this case, we'll have 4 rectangular subregions, each of which has delta x equal 2 and delta y equal 1. And we know that for each of these divisions, the outward flux is given by df1 dx plus df2 dy times delta y delta x. That's what we did previously. So now let's add all these divisions up. according to the divergence theorem, we should only be left with the flux that's leaving through the boundaries, the outside boundary, and all of the internal fluxes should cancel. So if we start here, this is outward direction of blue. So we're going to find the amount of flow from this vector field going outward along this line, plus outward along this line, plus outward along this line, plus outward along this line. Okay. If we go to this one, it's green, so we're going to find the amount of flow that's going leftward along this line, downward along this line, rightward along this line, and upward along this line. Those are marked in green. But if you look at this and this, the blue flow will give us the amount of flow across this line by this vector field going to the right. The green line will give us the amount of flow across this line of this vector field going to the left. We know those are going to be opposite each other. So this line is going to cancel. Similarly, if we look at the blue and the red, along this line, this division will give you the amount of upward movement of this vector field along this line. This division will give us the amount of downward movement from this vector field along this line. Those two are going to cancel. Similarly, this side and this side will cancel. So when we add up the outward flux of each of these divisions, we're going to be left with the amount of outward flux along the curve that encloses the entire region. So algebraically, that says if we add all these up, that will give us the outward flux, and that's sigma from I equals 1 to 2, j equals 1 to 2, df 1 dx plus df2 dy, evaluated at x1, y, xi, yj, delta y, delta x. And as we take the limit of those as delta x and delta y go to the 0, we get the precise value of the outward flux along this curve is equal to the integral from 1 to 5 dx, 2 to 4 dy, divergence df1 dx plus df2 dy. Okay. So we have a rather amazing conclusion that if we want the amount of flux that's leaving along a curve, we can integrate over an area.